In today's video, we're going to talk about section 10.3. This is part 3 in a 4-part series. We're going to finish talking about equation conversions. So recall, we will have a point r comma theta, and the r stands for it's a certain distance away from this pole, and the theta stands for it's a certain rotation away from the polar axis. But in reality, what we've done is we've mapped on the polar axis to the x-axis. This is just some length x. There's some height y. And this gives rise to our polar conversion equations. We have ones that are more useful if you start knowing the x and y values, like r squared equals x squared plus y squared, and that the tangent of theta equals y over x. Those are useful if you know x and y values. You can get r, you can get theta. But we also have the ones that are more useful if you already know r and theta, like x equals r cosine theta and y equals r sine theta. So in previous videos, like for part 1, we would have said, okay, I get it. We know the values, so now we're going to use them in these equations to get the other values. So the red ones are more useful for going from rectangular, the x and y stuff, to polar. And the blue was more useful if I know r and theta, polar, back to rectangular. But today's lesson, we're just going to try to use everything possible, whatever it takes. So let's do a quick example here. I have a line, example. If I have the line y equals 4. So again, this is not necessary to graph. This is more just an exercise in algebra and making sure you understand what's going on with the polar coordinate system. And that a lot of things that used to be polar and that a lot of things that used to be and a lot of things that used to be easy in rectangular are harder in polar. Just like we showed yesterday, things that were hard or impossible in rectangular are easy in polar. So this is easy in rectangular. Let's see what happens. So the general strategy is going to be replace the x's and y's and solve for r. We want r functions. R equals something with theta. So replacing x and y's are usually going to be easy because we have those blue equations right there. And now I want to solve for r. Well, I could just divide both sides by sine theta. And usually we don't like this reciprocal format, so I'm just going to rewrite it as 4 cosecant theta. And wow, that's a line, you might say to yourself. So what we have here is at theta equals 0, cosecant's undefined. We have no idea what to graph. But at pi over 2, cosecant's 1, so we have 1, 2, 3, 4. And what you would notice if you started giving a good effort here is that at different angles, no matter what you plug in, you get a value out of r that'll put you exactly 4 up. We sort of proved that this is true just now with our conversion. And then the same thing is true on the other side. Again, I'm picturing like radiating out, like a lighthouse, like a radar. And what we have is this horizontal line, but described in terms of how it transforms the angle away from the polar axis, the x-axis, the positive x-axis. All right, so let's do a few more examples. We have 3x minus y plus 2 equals 0. So again, when we're going from rectangular to polar, x's and y's, we're going to replace the x's and y's and then solve for r. That's the general idea. The next example will show one little wrinkle in this, but in general, this is what we got. So 3r cosine theta minus r sine theta, and then 2 we're not going to be able to replace. So in case you can't quite see what I've done, our cosine theta replace the x, and our sine theta replace the y. Really not controversial. It's just a straightforward application of what we had on the last page. I'm going to move the 2, and I'll tell you why we're going to move the 2, because I'm going to factor. Just like we would when we're trying to solve equations, like especially literal equations, we might need to factor an r out. To factor. So we would get r times 3 cosine theta minus minus sine theta equals -2, and then r equals -2 over 3 cosine theta minus sine theta. What's this graph? It's not easily done in polar. I know what it graphs. This is not really the point of the exercise to see what it graphs. To see what it graphs, you would look at the rectangular equations and you would say, oh, that's a line. Oh, a line. Is it clear that that's a line? No, it is not clear. If I just saw that guy laying on the street, is that a line? No. But I also probably wouldn't be trying to graph that in polar. If someone handed that to me, I might try to convert it back to rectangular, which is what we'll do in the next few slides. But not yet. Example 3. Let's talk about a slightly more interesting one. X squared plus y squared minus 2x equals 0. So there's a couple interesting things you can do here. A couple interesting ideas. If you follow the last example, and if you're already pausing the video and zooming through it, you missed this. You could try to replace it and go r cosine theta squared plus r sine theta quantity squared minus 2r cosine theta. So all of my x's got replaced with r cosine. Then what would you get? You'd have r squared cosine squared theta, r squared sine squared theta, minus 2r cosine theta. Then what? So then we could factor r squared out. Whenever we have cosine squared plus sine squared with the same coefficient, this trick works quite nicely. And when I'm saying something like this trick works quite nicely, you need to memorize this trick. This is very important, this step right here. Because it's the idea that coefficient cosine squared plus the same coefficient sine squared just leaves that coefficient. I'll write that down in case you are sitting there incredibly confused by what I just said. I'm going to solve it for r. You could have factored... Okay, never mind. Okay, I want to factor this. I want to factor this because we have a zero product situation. So this gives r equals 0, or r minus 2 cosine theta equals 0. R equals 0 is the equation of the pole, which is the origin. Is this, our equation that we started with, the equation of just the origin and polar? No. That's where we're going to rule that out. Now, part of the problem is some of you probably look at that blue equation at the top and say, I don't know what graph it is. How am I supposed to know what graph it is if the goal of this question is to graph it nicely? You're missing the idea. We don't have to know what that blue equation is exactly, although some of you should. What we need to know is that, oh, this blue equation represents something more than just the origin. In fact, what it represents is r equals 2 cosine theta, which, given the last video, this is a circle, diameter 2 on the x-axis. Center 1, 0. Half of the diameter is how I'm getting that 1. And that's what that is too in the blue equation. This is also the same circle. One more time, that's when necessary to rule out this r equals 0. It's an extraneous solution. Now, what I said over here in blue, this star, what I said over here with this star, what I'm saying is a cosine squared theta plus a sine squared theta. That factoring trick that I did is just a. It just leaves the coefficient because you would go a, just like we just did in this problem. We're going to use this fact a lot. In multivariable calc. So it's important. It's something worth memorizing. In the last video, we went backwards. In the last video, just to give you a brief overview of what I'm about to show you, we did something where we had r equals 2 sine theta. And applying what we just did, you should know it's a circle. You should know it's a diameter 2. And you should know it's on the y-axis because we have sine. And so it's 0, 1, the center. So you can see the last video for a more thorough explanation. I'm just trying to put this in this video because I want to have everything all in one place for you. So what we have here, one technique that's helpful is if you just have sine or cosine, multiply by r. Why? Multiply both sides by r. Because then we end up with r squared on the left and 2r sine theta. That's why we're going to multiply by r. Because then I know this side is x squared plus y squared, and our other side is 2y. Okay? In terms of homework, in terms of tests, this is a polar equation. If we do a bunch of work, this is a rectangular equation. I misspoke. In terms of a test, this is a rectangular equation. So if I ask you a rectangular equation, if I ask for a rectangular equation, this is okay. But with a lot of work, you can simplify it down. It's not that much work. It's a little technique called complete the square. You'll be fine. This is in the last video if you want to see it. See previous video. Okay, so if you're looking in the book's answers, this might be the answer you see. It's just from completing the square. These answers are equivalent. The thing I want to mention here, just so it's all in one place, multiplying both sides by r. If you have just sine or just cosine, that'll turn to r sine, which is y, or r cosine, which is x. All right, let's do a few more examples. R equals -2. All right. When you have r equals -2, I do not recommend multiplying both sides by r, okay? We don't have a nice equation for 2r. I have no idea what that would represent. But I do know that r equals the square root of x squared plus y squared. Now, there's going to be an issue. So if I just replace r with x squared plus y squared inside the square root, I'm going to point out that this is a big warning. This is not a possible equation. Because a square root, this side can't be negative. Not just because the inside can't be negative, although that's true too. A square root never outputs a negative value. Okay, not with a positive coefficient like that. So you must square both sides. And some of you might be saying, well, Mr. Levin, I can't believe you're saying that. You always tell us to be careful about squaring both sides. I'll say more about that in a second. The reason we're squaring both sides is to reflect the fact that we couldn't have this red situation. I'll also say a few things. This is a circle with radius 2, centered at the origin. And so is r equals -2. R equals -2 in polar, okay, that's the idea that I want to go with a radius of -2 at the angle of 0. And then -2 at the angle of pi over 2. And then -2 at the angle of pi. So it's just a circle that starts in the wrong location. It's still that circle with radius 2. It's the same graph. Goes back to the redundancy of polar information. Just be very careful here. You do not want to mess this up too much. I mean, you don't want to mess it up at all. I don't know why I said too much. Let's move on. Last one. And then this might go without saying. I kind of think that if I left you all to your own devices, you would figure this out. But if we have cosecant or secant, and this might apply for tan and cotan, convert to sine and cosine first. What do I mean by that? And you might be ahead of me if you're thinking about what we started with. Okay, so I have 2 over sine theta. How's that help me? Let's multiply both sides by sine. And then wouldn't you know it, r sine theta, that's y. And so again, we have a horizontal line at y equals 2. Okay, so that's it for polar conversions. I'll see you in the next video where we'll finally talk about polar equations with tangent lines. All right, see you next time. Bye.